Welcome back. So, let us resume our discussion. Now, once we have this W by L ratios available and the GM1 available, we need to look at the gain. What is the gain requirement? So, if I look at the say next requirement of gain, let me keep this sequence over here as it is, and let me go to the next requirement, which is the overall open loop gain that we are looking at, and also the corresponding bandwidth. So, we have the open loop gain requirement, which is around 10 to the power of 4, and once again we can divide this in an uneven fashion. We can take a smaller fraction of the gain for the first stage and larger one for the second stage, or vice versa, and that also depends upon design considerations. If you are going for say larger gain for the first stage, once again it basically contradicts with the noise requirements. So, for the time being, let us bifurcate the gain requirement also equally. It is not a bad choice, and you can do that, especially for low power applications where the current budget is the deciding factor. So, let us go for the equal partition of the gain between the two stages, and then say that A1, A2, the gain of the first and the second stage, each is going to be given by around 100. So, that the overall open loop gain of the amplifier is 10 to the power of 4 as we need it, and that would mean that GM1 times RO by 2 of the first stage should be 100. The GM1 has already been determined in the previous stage based on the gain bandwidth requirement and the CCCL requirement, and therefore, the RO can be obtained from here. So, I can obtain RO of the input device. Now, RO of the input device does not mean that you have both the ROs coming into picture. The RO which is smaller, that will be coming into picture while determining the gain of the first stage. So, once again, just for sake of convenience, I am drawing the entire circuit, and the RO in the first stage is going to be the RO of the smaller RO of these two. So, first stage RO is going to be determined by RO P parallel RO N for the differential operation, and assuming that the bias current in both of them are similar, the RO is going to be dictated by the channel length. And if we recall our discussion on noise, we know that the low input referred noise requirement asks us to keep the channel length of this PMOS sufficiently large, because that appears in denominator as L square when we are looking at the input referred noise V in square. So, the channel length of the PMOS must be significantly larger. As a result, the RO of this PMOS can be pretty large as compared to the RO of the N. So, for noise requirement, for noise constraint, I would generally have, if I call this input pair M1 and the PMOS M2, I will generally have the RO2 much greater than RO1. It can be at least 10 times greater than RO1, and as a result, the gain in the first stage is going to be determined by GM1 RO, really RO1. So, I should to be more accurate, I would say the gain is GM1 RO1, and that would give me the value of RO1 estimated. So, this gives me GM1 RO1 equal to 100, and with the known value of G1 I can get the value of RO1, and we know that RO1 is equal to 1 upon lambda ID, which also depends upon the channel length. If you remember, we discussed in the very beginning while discussing the device concept that the lambda is can be expressed as lambda dash upon L times ID. So, if your channel length is larger, effective channel length or effective small signal resistance increases. Therefore, the L over here can be estimated based on the value of ID and the RO that we have. So, ID we have already got from the power budget, this came from the power budget, and RO1 came from the gain requirement, and hence I can get the L1, the input device channel length, from this constraint. And once we get L1 from here, once we get L1 from here, we can get the W of the input device also, because from the GM constraint. So, once we have for L1 obtained above, we can get W1 from GM1 because again the GM1 is nothing else but root under 2 ID 1 mu n COX W by L1. So, since L1 is known, ID is known, I can find out the W1 required. So, I have the input device sizes for the first stage. Now, likewise, if I have the value of GM1 and also the GM2 known from the previous step, if you recall, the GM1 GM2 ratio also was known depending upon the C1 CC and CL ratio that we set. So, CC CL ratio was determined based on area constraints, and based on that I determined the ratio of GM1 GM2. GM1 is known, GM2 is now also known, and therefore I have the current budget. I also have the current budget given to me. So, I bias of the second stage is also known to me. I have bifurcated the current into two halves. So, here also I have the total current bias given by 10 microampere, here 10 microampere, and both the branches 10 microampere, leading to total to 40 microampere. So, each branch is having 10 microampere of current as our initial assumption, and therefore, I have the W by L requirement of the second stage as well. So, from this I can get for GM2 assumed earlier, I can obtain the value of W by L2, GM2 and ID2. So, GM2 and ID2 that we obtained earlier, from there we can estimate what is the value of W by L2 required. Let me rather call this 3, let me call this pair as 3. So, this is 3 3, this is 2 2, this is 1 1, or I can stick to the Roman letters just to be consistent with my notations. Let me stick to the Roman letters because I am using the Roman letter to determine the stages. So, the Roman letter 1 determines it means the first stage, Roman letter 2 means the second stage. Let me stick to the Roman letter and say that the GM2 also I can denote it by the Roman letter. GM2 will be obtained by the GM1 GM ratio that we had over here, and from there I have the ID2 also determined, and I can look have the value of W by L2 known. Now, once we have the W by L2 known, there once again we can look at the overall sizing constraint or the L values for the PMOS and NMOS devices. As we have seen, the 1 upon f or thermal noise of the second stage does not interfere so much, does not reflect so much as the input referred noise, because it is getting divided by the gain of two stages GM RO square, and therefore the channel length sizing constraint does not come here so strictly, and therefore these channel lengths can also be similar. I do not really need to have very skewed channel lengths as in the case of the first stage. In the first stage, however, as we have seen, the channel length of this device needs to be determined based on the 1 upon f corner frequency. So, if you increase the channel length of this device and also the W of this device, you can shift the corner frequency towards lower value. So, if you remember the 1 upon f corner frequency derivation, it will be determined by the channel length of this and the W and L, WL product of this. So, if the area of this input device is large, we know that the flicker noise is proportional to 1 upon WL, and this flicker noise of this input device directly comes at the input. So, for that I do not even need to do any derivation. I know that the flicker noise is proportional to or inversely proportional to 1 upon W times L. So, I would like to increase the WL product so that I can minimize the input referred flicker noise of my first device, or in other words minimize the corner frequency, shift it towards lower values. So, shifting corner frequency, why it is important? Because it will allow us to have a lower chopper frequency and hence lower bandwidth. So, for as of now we have targeted that let us keep the chopping frequency 100 hertz, and if it can be met comfortably within this 10 microampere budget, we are happy with that. If you are still having more budget available, you can further try to shift it back towards lower frequencies by increasing the channel length further and W by L further. But for the time being, the initial target is just to check whether with the W1 and L1 that I have arrived at, and by increasing the L of this device towards higher values, how low I am able to shift the corner frequency. So, I have the W and L of this input device already determined by the gain requirement and the RO requirement, and the next is the W and L of this. So, as we said, the L of this device can be increased, we can try to push the L towards higher value, and that will help me in reducing the 1 upon f corner frequency towards lower value. What is the possible disadvantage of that at the first stage? So, if I consider the noise issue for, let me just keep this circuit as it is. If I look at the noise issue for lower FC, I would like the L of 2 to be large and also W1 times L1 to be large, both these factors. And if I increase the L of 2, we know that the overdrive voltage of M2 will be increasing if I am increasing the L of 2. That means if the W by L of 2 is reduced, the required VSG to support the same given bias current will be increasing, and as a result you will require a larger VSG drop, and that would mandate that your overall signal swing at this node gets limited, right. So, if you are having larger L, means W by L of M2 getting reduced, sorry, so W by L2 getting aggressively reduced because you are pushing the L2 larger and larger to get the 1 upon f, right, so reduced, and that is going to require a larger VSG drop. A larger VSG drop, that means the gate voltage, the gate bias voltage over here is going to be lower. Gate voltage over here lower means the maximum potential that you can have over here, that is also going to be lowered, right, because we know that the maximum potential available at the drain of these two outputs is going to be VGP plus mod Vt. So, a larger L of these devices and smaller W by L of these devices, larger L means larger VSG2, and that would mean smaller VD2 max, because VD2 max is equal to VG2 plus mod VTP, right, because if you are requiring larger VSG, that means smaller VD2 max, because the VD2 max is VG2 plus mod VTP. Larger VSG means smaller VG2 and hence smaller VG2 max. But is that a serious constraint for the first stage? Especially if you are looking at the input stage and the signal swing is relatively small, 100 microvolt, and the overall closed loop gain is say 100. So, at the max we may be getting a signal of 10 millivolt at the final output, and for that 10 millivolt we are having even further smaller signal swing over here. So, final closed loop gain, if I look at a closed loop gain of 100, the amplifier at the output will be producing 100 micro times 100, and for that 10 millivolt the input swing over here will be further 10 divided by 100, so 0.1 millivolt. Therefore, the swing over here may not be a serious constraint. Therefore, having a larger channel length for these two devices and having a smaller VG and hence a larger V over drive is not a significant disadvantage. So, that is also we should keep in mind. So, for the input stage, noise minimization is going to be crucial. Having a smaller swing is definitely not a constraint. Even for the output stage, you are having just 10 millivolt peak to peak swing at the max, and therefore, the signal swing at the output is not a major constraint. So, even if I have to choose larger channel length for these two devices in order to increase the gain higher and higher, is definitely going to reduce the swing. For given bias current, if you increase the channel length, the required VG of this gate also goes up. Likewise, the gate voltage of this NMOS goes down. So, if you are trying to increase the channel length of these devices also, for example, to get larger gain for a given current. So, for a given current, if you increase the channel length, the RO will go up, and as a result the gain can be expected to be higher. But once again it is going to reduce the available signal swing, but that is not a significant constraint for the first stage, and therefore we can sacrifice the signal swing, we can ignore the requirement of the signal swing while focusing on noise minimization, while focusing on lowering of the 1 upon f corner frequency. So, let us just assume that this W and L1 is sufficient for giving us sufficiently low corner frequency, and then I try to maximize the channel length of the M2 so that a desired 1 upon f corner frequency is achieved. So, you have, remember, if you have the W by W times L1 coming in the first bracket, and then you have the second one which is having L2 square in the denominator. So, I would like to for a given W1 L1 I would like to maximize L2 to basically check that a desired 1 upon f corner frequency is met. After that, once you have L2 determined, once you increase the L2 such that the 1 upon f corner frequency shifted further down, then the question is for determining the W of these two transistors, and once again it is not going to be a serious constraint. So, W2 can be set to obtain, say, the V out over here, V out 1 DC, say close to at the max say VDD minus 2 V overdrive, or VDD this can be a sufficient number. So, if the V overdrive is the overdrive voltage for this PMOS, I can set the W by L over here, so that the desired DC potential over here can go down. So, if I am looking for the maximum allowed potential over here, and I would like to set it to say close to even VDD minus 2 V overdrive, where V overdrive is the required V overdrive for these transistors. In that case, I can accordingly set what is the W by L required over here. For example, for the second stage, if I look at it, I already have the W by L required from the previous equations, and I also have the ID required. So, that is going to give me the required VSG for these two devices, and that VSG is basically the drain potential of this one, and I would like to make sure that that drain potential is sufficiently low for the PMOS over here. So, one possibility of sizing the W by L of M2 is get the VG3 from the ID 2 and W by L 2 determined from the previous stage. And once you have that, then basically we have the VG VD3 VD2 required. So, we have this VG3 equal to the VD2, and corresponding to that I would like to make sure that this VD2 is not too high for the M2. So, I would like to make sure that VD2 over here is lower than VG2 plus mod VTP2, and that means I can obtain the value of VG2 required. VG2 should be greater than VD2 minus mod VTP2, and that is going to give me the VSG requirement. If VG is greater than this, then I know that VSG2, which is VDD minus VG2, must be smaller than VDD minus VD2 minus mod VTP2. So, this is another this is one way in which you can arrive at the VSG2 requirement, and that is going to give me the W by L requirement of the two transistors. So, I already have the L determined from 1 upon f noise, and then I can set the W of the two transistors following this equation. So, I have the VSG requirement coming from the expected gate DC potential, and from there I can set the VSG2, and that is going to give me the W by 2, because you know the W by 2 is going to be determined by the VSG of the M2. So I already have L2 known from the 1 upon F analysis, corner analysis, and then I have W by L2 known. So that basically gives me the W and L of the PMOS transistor over here, and I also have determined the W and L of these devices, assuming that they are meeting my 1 upon F noise criteria. And finally, the L of these devices, W by L is known for this input device. I need to check the L so that the gain of 100 is met in this stage. So from A2, I can determine the gain. I can determine the RO of the output device, which is going to be given by GM RO by 2. So get the RO 2 and hence get the L2 for determined W by L2 of the second stage. So W by L2 has already been determined previously. I have the A2 known for the second stage around 100, and therefore RO2 known, and that is going to give me the L2 for a given W by L2 and ID2. So that basically gives me the W by L2 of this device, and also the W and L individually. So I have the W and L of the M3, M2, M1 known. Now the next is the question of this NMOS devices. So for NMOS devices, once again the channel length should be similar for the second stage. For this, if I look at the second stage, if I call this say 1, 2, 3, 4 M4 pair, that means I am calling these two as M4. So once again the RO is determined, I is determined for a gain requirement. Therefore the RO2 determined earlier sets the L2 or L4. So L4 is already known, RO2 and ID2 determined earlier sets the L4, because ID2 budget is known, and also the L4 has been determined based on the gain requirement. So that gives me the L4 also. So these two must have same L4 so that the RO is equal to the required value, so that GM RO is equal to 100. And next I have the W of this MOSFET to be determined, and again W will be determined by the output signal swing required. I must make sure that the output minimum level required over here is higher than VG4 minus VT, and that gives me the VG4 constraint. So V out min is VG4 minus VT, and therefore VG4 V out min should be greater than equal to this quantity, so that this M4 does not enter into triode, and therefore VG4 should be less than equal to V out min plus VT. And once again the V out min, if I call this V out min is not going to be very small, because output DC point can be VDD by 2 and V out min can be hardly VDD by 2 minus 10 millivolt, and therefore this is also not a very important constraint, and therefore the W by L requirement of M4 is not very significant in this case. I can have a poor W by L of M2 also, or W can be pretty small, is not very important. However, the tail current source, once again, for, if I call this M5, for M5, what is the W by L constraint going to determine? If the W by L of M5, if we keep it small, then the required VG value will be large for a given bias current, and that means the minimum input level that you can have is going to be small. So the gate level or gate potential of M5 determines the input common mode range. What is the minimum input signal level, whatever the minimum input DC level that you can have. In our application, if you remember, the gate DC potential is being determined by the output DC potential, which is equal to VDD by 2 using the resistive feedback, and hence the input DC point over here is fixed. We are not having DC coupled system. So input is coupled through the main amplifier using capacitive feedback, and this is the DC potential over here is determined by the output DC potential, which is VDD by 2, and input signal is pretty small. It is just a few tens of microvolt to 100 microvolt, and this is going to be not having any significant signal swing.